Everybody. Here's the final video in our series on logistic regression. This is some additional useful statistics. We'll take a look at what's called the likelihood ratio chi-square for coefficients, and a statistic that's analogous to R squared called R squared L. All right. Test for coefficients. We've been looking at a test for the significance test for coefficient that is printed as a Z statistic. This is commonly called the walled Z. Some programs will present this as a chi-square statistic with 1 degree of freedom. Chi-square is equal to Z squared. So you'll see both forms used. This is the most common statistic for statistical packages, but it's kind of unreliable with small samples. And what happens is standard errors tend to get really inflated in small samples. I also see this happen with complex models, sometimes with interactions. So those statistics aren't the best under all circumstances. I don't think they gave us much of a problem in this set of this set of analyses, but certainly they can be problematic. The preferred test is what's called the likelihood ratio test, or likelihood ratio chi-square test. It's a minor pain to calculate. What the test does is it's basically looking at the difference between a full model and a model with all but one variable in it. And now the variable that's not in the model compared to the full model gives you an index of how much this variable is contributing over and above the other variables. It's very much like a change statistic in hierarchical. If you imagine one model having all but one variable and then one model having everything else, this would basically be equivalent to an F change statistic. So one of the challenges here is this means that not only are we going to have to run our full model, but we're going to have to run a series of different models. We're going to run a model that has everything but barriers, a model with everything but benefits, a model with everything but knowledge, a model with everything but physical recommendation. So that's what we're going to be working with. All right, so the first thing that we need to do here is build the full model, and I've called that model 4. It's got all 4 variables in it. I named the rest of them for the variables that got left out. So if we look at, say, model phys, we're predicting compliance from knowledge, benefits, and barriers. We're leaving out physical recommendation. I then did that for all the different combinations. My knowledge, model no, model benefit, model bar are leaving out. Sorry, my cat just went nuts. Are leaving out all but one, variable. So we run all of these models, we build them, and then we have to compare them to each other. And that's what this command called the LMLR test from the LM test package does for us. This is how we do it for the first value. I simply enter the full model and then the model that has all but the variable of interest. This is going to work for a physical recommendation. This yields a chi-square value with degrees of freedom. For some reason, the degrees of freedom are negative, but it should just be degrees of freedom of 1 there. That is represented as negative, but it's a degree of freedom of 1 actually. The chi-square value is 16.67. It's significant, well below 0.001. We then need to run this for all of the different predictors. So we're going to have 4 different tests here. This is the test for just physical recommendation. You can see the rest of them. Here is the test for knowledge. The first one, we can see knowledge is not significant. For benefit, we can see benefit is significant with a probability of 0.02, and then we can see barrier, the final one, is significant. It's probability less than 0.001. Again, the reason why we do this test is that this test is more stable across a host of situations. The Z test that we get can sometimes go a little crazy. We'll see situations where we have gigantic standard errors. It just gets misestimated at times. So the logistic regression chi-square is preferred. Even though it's the preferred test, it's still kind of a pain to get these values. Just comparing the different values, this is a situation where we really don't have much of a difference depending upon the sort of test that we use. The differences here are, or it looks like we don't have much of a difference in terms of the probability values. That's true and not true. These are actually somewhat different estimates. We can see the logistic regression, I'm sorry, the likelihood ratio chi-square for physician's recommendation is 16.67. If we were to convert the z-value that we got to a chi-square, it would be around 15. So you can see that there is a difference in estimation there. And the way I converted that z-value, just squaring 3.77. So we can see that we are getting a slightly different estimate. It doesn't really make much of a difference here. In fact, for knowledge, we get exactly the same probability. In fact, for benefits, a little bit different in terms of the probability values. But again, logistic regression is generally going to be better if we use this likelihood ratio chi-square. All right. There are a lot of statistics that have been presented as analogs to R squared. One big difference that we've seen here in terms of linear regression is that we don't get an R square value for our overall model, and that was kind of the first thing that we would look at with linear regression. So there have been a lot of different R square analogs proposed. If you look at a book on logistic regression, some of them even have an entire chapter dedicated to these different statistics. Perhaps the two most popular R square analogs are the Cox-Snell and Nagle-Kirk R squares. I've always been suspicious of these statistics because they give really different answers. These are likely very popular just because SPSS has these values, and people just think that those are going to be the best because of that. The consensus, though, is that the likelihood ratio R squared, R square L, is going to be the best measure, is the most stable across situations. That's the general conclusion that's been drawn in the logistic regression literature. The formula that you see for that value is, it's a little scary looking. It's -2 LL baseline minus -2 LL model minus -2 LL baseline. That's actually not as scary as it looks. -2 LL is just a chi-square statistic, and in fact, these are chi-square statistics that we already have. So the deviance statistics are the -2 LL values here. That's just those chi-square values. Null is the baseline model, and residual is the one for our model. You can see I got the calculation there. We're just taking the two chi-square values, the difference between the two, and dividing by the baseline, and this gives us a value of 0.259. I've added code down below. You can get R to do this for you. Once you've built the model, those statistical values are in the model. You just are taking the difference and then dividing. So you can do that either way. The one interesting piece here is that this R square value comes out to 0.256. I didn't provide these with code, but just for comparison, the Cox-Snell R square value would be 0.301, and the Nagle-Kirk R square value would be 0.402 for this model. So you can see that there's kind of a wide range of values there, big differences. I think one of the reasons why people tend to report Cox-Snell or Nagle-Kirk is that those two values tend to be a lot bigger. They look a little bit more impressive, but again, the likelihood ratio R squared is going to be the way to go. So again, useful piece to report along with that model significance. All right, this takes us to the end of our logistic regression section. Some useful resources for learning more about logistic regression. Andy Field's AdventR package has a tutorial on logistic regression. It's relatively short, but it's certainly worth checking out. you'll have to install that from GitHub. There's some instructions that I'm passing along about installing stuff from GitHub that we can check. One of my go-tos is always UCLA Statistics, Statistical Computing. They have data analysis examples for many different software packages. R, of course, is a big one there. I like those because I like seeing actual examples worked out to give a sense of how to run stuff with code. And of course, the handout, our class handout on logistic regression, of course, a useful resource, has some additional examples and kind of a little more exploration of the odds and log odds if you're interested in that.